Today we're going to be finishing up the info on the sol gel, and we're going to start talking about surface areas and how to measure them. Objectives for today for the sol gel side: be able to identify and describe ways to dry a sol gel. So last time we were talking about all the different ways to make a wet gel, but then how do we actually dry them and get a nice aerogel? Identify the pros versus cons of each different way. Then be able to identify the source of drying stress. We'll discuss this, but basically, why is there stresses involved when you dry? Then, for BET, also known as nitrogen absorption, which is the best way really to measure the surface area of a material, be able to describe just how it works, the process by which nitrogen absorption tests are able to characterize the surface area of a material. Also be able to predict the outcome of a BET test under given conditions. So if I give you two different materials and tell you their properties, be able to predict what the BET curves might look like, at least just relative to each other. We'll get into that. First, let's finish up the sol gel and talk about gel processing. If we were to take our solution of sol and spin coat it, which is a rather neat trick actually. Take a disc of a substrate, put it on a motor and spin it, and then drop your sol solution. So actually really dilute solution of your sol before it gels. Just let it drop onto the surface as you spin. It'll coat the surface and any excess will fly off. As it's doing this, it's also evaporating and densifying. And what you get on top of your substrate is a very dense, thin layer of your sol. But instead of spin coating, what if you let that sol gel? So you cast it into a mold and then you let it gel into a rigid shape, just like we showed in class with the vial that we passed around. So you get those MERs that were in solution, they cross-link and form a stable gel, solid network region from one side to the other. Awesome. Now it's filled with liquid, and I'm just going to color on the top there, so we're using the same color scheme. Now it's filled with a liquid. Those pores are filled with a solvent, with the expanding solvent, but what we want is a dry gel. We want it to be completely dried, so we want to replace that liquid with a gas. If you were to take a solid surface and put it into a liquid, take a tube, what does the liquid do? It rises a little bit. It rises a little bit because of the surface tension of the fluid makes it want to basically coat the glass surface, so it rises up a bit. But what happens if you have an even thinner tube is it rises up even higher. And a very thin tube, it actually rises up quite a bit. The shape of the material is what is causing this fluid to rise up so high. And really the only thing that matters is the diameter. The diameter or the radius of these tubes are what determine how high up that liquid rises. Specifically, the pressure of the capillary forces is equal to 2 times the surface tension of the solvent being used, times the cosine of the angle, that angle right there, divided by the radius. So there's an inverse relationship. The smaller the radius of these tubes, the higher the pressures, the higher the forces they'll be exerted. In our aerogel, those tubes are our pores, which are 10 to 100 nanometers, which is really small, which means our forces are really big. We have the act of these drying causes such great force that it actually compresses our gel. The little bit, the 3% silica that's in there, is not enough to resist those forces. So when we start looking at it as it dries, it shrinks. It shrinks and shrinks and shrinks until it's fully dry and it's a very, very dense little puck at the bottom of our glass. If a sol gel is dried like this ambiently, it is termed a Xerogel. Everyone has their own fancy names for these things. And it is very dense and very, very small pores, angstrom to maybe 1 nanometer size pores. But it's very dense. We've lost all that nice porosity that we had. So, what if you were to do a different method called supercritical drying? This is the way we get aerogels. This allows us to dry a wet gel without the pores collapsing. So somehow we've defeated that problem of capillary pressures causing the entire thing to just compress in on itself. That we've found some way of getting the liquid out and replacing with the gas without the liquid evaporating. Let's look at how we do this. Take a pressure temperature diagram. You may remember, so we have temperature on the bottom and pressure on the top. So this is a phase diagram, and we're going to chart the process that our pore fluid takes. So phase diagram has split into three components basically. We have a solid phase, a liquid phase, and a gas phase. And any point within those areas at that temperature and pressure, you are in that phase. Our Xerogel we got because we started with a point that was just inside the liquid area. So we have our liquid, it's at room temperature, but it wants to evaporate, which means it's at a high vapor pressure. So really it's trying to get down to room pressure, which is down here and this point down here. And in order to do that, it's evaporating. It's crossing that line between the liquid and the gas. That's the line that separates those two. So anytime you cross that line, you basically will get evaporation. Evaporation leads to capillary forces. Capillary forces leads to pore collapse, and your gel densifies. So we need to find some way to get from the liquid to the gas phase without crossing that line. And one of the neat tricks about a phase diagram that they usually don't tell you is that line ends. There's an ending point. And beyond that, you're in a phase called a supercritical fluid. It's kind of a tricky thing to describe, but basically it's not a fluid, liquid, it's not a gas, it's some combination of the two. If we take our liquid and we raise the temperature and pressure to go into that supercritical fluid phase, let the pressure off and then let it cool back down, we can go to our room temperature, room pressure, gas phase without crossing that line. So we never evaporated. We never there's no evaporation, so there was no boundary between liquid and gas. There was no surface tension. There was no capillary forces. The other way of doing this is the other route. Freeze it first and then pull a vacuum, which is more commonly known as freeze drying. This is how they make astronaut ice cream. This is how they make the fruit that's in your breakfast cereal, the strawberries. Those are freeze-dried fruit and freeze-dried products. The problem with freeze drying is you don't get that strong of a gel network. The process of freezing, turning the liquid into a solid, causes crystals to grow, and those strong crystals break your silica structure, so you get a lot of cracks and fractures and misshapen gels. But it's still a neat process. So if we supercritically dry our gel, it's termed an aerogel. And if we freeze dry our gel, it's termed a cryogel. So we have Xerogel if you ambiently dry, Aerogel if you supercritically dry, and Xerogel if you freeze dry. Like I said in class, everyone likes to have their own names for these things.